Okay, we'll begin. So thanks for coming out this morning. I'm going to lecture on the last two classes for Signals and Systems in the fall of 2014. And primarily what we're going to be talking about is Z-Transforms. If I run out of things to say, I have a short review of the course as well. But again, that's I'd rather cover the materials on Z-Transforms, and I think you guys would too. All right, so let's begin. Last time we talked about sampling of signals. So I'll just draw a picture to kind of remind you. And when you sample a signal, you basically take points and you turn a continuous time signal, I think, what did I call it, W of t last time? And you come up with a W sampled of n. So so sampling turns a continuous time signal into a discrete time signal. And notice that you're not yet at the digital. You don't yet have a digital signal, right? Because you have to, for a digital signal, you have to quantize or discretize the time axis, and then you also have to discretize the z-axis. Okay, so this is a discrete time signal, and the discrete time signal is not quite exactly the same as a digital signal. Okay, but no matter. This is the WS of n is the discrete time world is really what we're going to play around with this morning. And so what I'd like to do is I'd like to just start with the most general discrete time signal. And I'll just remind you that so each one of these spikes, each one of these sampled signals, can be represented as a delta function, and then the height of these delta functions is given by a sub k. And what's important is this k here. This k here tells you which delta function you're talking about. This k is exactly a delay. Okay, remember that we learned about that in Chapter 1, I think, in our transformations of a signal. And I want to remind you of the fact of this delay, because this is absolutely key with what we're going to be talking about today for the Z-transform. And remember that the Fourier transform for a delay is e to the minus I delta. Okay. So you Fourier transform the function, and then the delay part of it comes out as an e to the I delta. And I always think of that e to the minus I delta as a time shift. But many people, and this is absolutely true, it's a phase shift as well. It's a phase shift as well. So you can kind of think a little bit about the differences between a time shift and a phase shift. At the most trivial level, they're exactly the same. But a phase shift is usually normalized with respect to frequency. So you talk in terms of how many radians of a phase shift versus how many milliseconds of a time shift. So units are a little bit different. So importantly, when I want to represent this guy in a transformed space or in a frequency space, the two pieces of information to keep track of are the weight, the coefficient, and the shift when that weight or when that delta function comes. Those are the two pieces of information, term by term by term, that we have to consider. So the trick or the dirty secret, this is probably not as rigorous as most people would do, but the dirty secret of the Z-transform, as far as I'm concerned, is you set a small variable change of z equal to I delta. Okay? And so then, therefore, this transformation goes to a z to the minus 1. the delayed term, the delay term in the Fourier space goes to a z to the minus 1. And that is about as simple an explanation of what we do when we Z-transform. And it may over-trivialize certain things, but it's really something that you should keep in your back pocket because it sort of completely demystifies what a Z-transform is. And for that reason, I think it's really good to let you in on that little secret. Okay? So now, if I put all this stuff together, I have x of n, and remember what we want to do is we want to transform x of n into a frequency space. And so if I keep track of the delays through this z term, then I'm going to have the transform x of z. So x of n will transform to x of z, and I'll have a summation, the same summation that I had before. The a sub k's just go along for the ride, and the delay terms are represented exactly by a z to the minus k. So we now have a polynomial. We now have a polynomial in z space, in our new variable z. Okay? So aside from the notation, there's really very little going on here. You know, we're just taking the delta functions, and we're making and the transform of the delta function delayed is just z to the minus k. Okay, so really, the thing to notice is that this z to the minus k is a shorthand for a delay or a shift in time. Okay, and you can think about a little bit about why that's a reciprocal space. Okay, for a little bit, but okay. So that's our starting point, and these two things then form your Z-transform pairs. Okay. Now let's do a quick example. The way we set this up, nothing can be simpler, and it really won't get much harder. Trust me. That's why the Z-transform is so darn powerful and so darn nice to work with, because it is so slick and easy to work with. So let's do a quick example. And I just kind of pluck these out of thin air. So 3 delta functions, 3 sampled points. If I plot this, n equals 0, n equals 1, n equals 2, n equals 3. I have a point that's 5 units tall at n equals 0. 3 units tall at n equals 1, and 1 unit tall at n equals 2. And if I write this in the Z-transform, I look for the k's. In this case, this is a delta function that's shifted by 0. So my first term is going to be 5 z to the minus 0, which is particularly easy to evaluate. The second one is n minus 1, and that's a delay of 1. So I'll have a weight of 3. That's my a sub 1. And it will be z to the minus 1. And my last term is 1 times z to the minus 2. So that's my Z-transform of that signal. And I can represent this signal. Perhaps remember this can also be a transfer function, right? For a linear time invariant system. So I can it's not outrageous to try to think about how to generate this signal. And so if I think a little bit about it, I'll start with a delta function to generate this signal, because all my my terms of my all my terms of my signal are all built around delta functions. So I'll start with a delta function. And what I want to do is if I want to generate this term, I need to have that delta function come out of my box instantly. So I will send this, but I also have to scale it by a factor of 5. So I'll put some sort of a gain element in there. And that will come out of 5 times the delta function. 5 times the delta function will land out here exactly, without delay, exactly at time t equals 0. I also need to build a 3 and delay it by 1 unit. So I will take my delta function and I'll branch it off and I'll delay it by a block z to the minus 1. This notation is small and huge in impact. Okay, so this is a delay block. And I will scale it by 3. And I will feed it up to there. And so now what will come out will be a 5 delta function plus a 3 z to the minus 1 term, which is the second term of my signal. And then I also want one more signal. So I'll take this and I'll go through 2 blocks, scale it by 1, and I'll come up this way. So this path will delay it by 0, this path will delay it by 1, this path will delay it by 2. And that's one methodology, or that's one block diagram that will generate this delta function. Okay? And so these two pieces are the delay blocks. And we'll learn to be a little bit more economical in our block diagrams for generating these delays. But this is a very explicit formulation. Now, there's some classifications when we start looking at these filter flows. When we start looking at these signal flow diagrams, these ways of transforming one input signal to another output signal. That's the filtering problem. When we start to think about it, we like to classify them, and this. If you look through all of these feeds are feed forward. Okay, so they all flow forward in the signal one. So we call this a feed forward structure. Okay, so that's just a little terminology. Now, it's a property of all feed-forward structures, and this one is no exception, that I send in a delta function, and what comes out is an output of finite duration. There is no delta of n-3, n-4, n-17. If I fed back, if I had a feedback loop, and I'll show you examples of this later on this morning, then by all means you're going to have an infinite sum. An infinite series coming out. But for a feed-forward structure, you always have a finite impulse response, or an impulse response that is truncated in time. So this is equivalent to calling this a finite impulse response structure or filter. And we abbreviate that FIR. Okay? So a couple of terms of art that are sensible and help us out in understanding this thing. Okay, let me give another example. Let me give another example, and I'll do my simplest feed-forward structure. So I'll have an input x of n, an output y of n. That's equivalent to an x of z and an output y of z. And you see that this signal gets delayed. And so there's a signal that flows through straight, and then there's a signal that flows through and sees 1 unit of delay. There's no weighting there, so these come in at exactly the same weight amplitude. So I have y of z is equal to x of z, and just skipping exactly one step of mathematics, I have a 1 plus z. So x of z times 1 is this path, x of z times z minus 1 is this path here. Okay? So I've skipped a step, but it's not too terrible. And you might leave a space and fill it in if you'd like. Well, remember our work with transfer functions. In the frequency world, h is just y over x, the output over the input. And if I go back, if I now reinterpret z to the minus 1 as my delay, then this transfer function is 1 plus an e to the I delta. Which is equal to 1 plus cosine of delta plus I sine of delta. Euler's relationship. Okay? And if I want the magnitude, I'll be a little careless about what space I'm in now, because I seem to be straddling somewhere between the Z-Transform and time and frequency, and that's purposeful, right? That's purposeful, blending these perspectives together. It's the same structure. So my magnitude is going to be my real part, 1 plus cosine of delta squared, plus sine squared of delta. That's the imaginary part squared. And I'll go ahead and just, let's see, that's going to be del squared, because I should square root that. If this is a voltage signal, and I square root this, I get back to volts. If I don't square it, I have V squared, which is proportional to power flow. So that's why a lot of people don't square root things again, because they're looking at the power transfer from one input to output. Okay? And so if I work all this math out, twice cosine of delta plus cosine squared of delta plus sine squared of delta, these two terms add up to 1. And so I'm left with a DC term plus a cosine term and if I plot this is a raised cosine response. DC shifted, a cosine shifted up. This starts at 2, this is 0, and this guy here happens at pi. And remember, this is my output to input. And so if I come in with a signal like this, I'll come out with a signal like that. Okay? If I slide my signal over here, I'll get a clipping. If I slide it here, I'll get another clipping. If I do it right in the middle here, I have an approximate linear input to output. Not quite linear, but approximately linear. And this is actually an interesting place to run this device. I might have mentioned that my area of study is in optics and photonics. And what I've just described for you, this example that I've just described for you, is something called a Mach-Zehnder interferometer, which is interesting in and of itself, but this is actually much more commonly used as a modulator. And so this is the basic building block of all the modulators of all the fiber optic systems that are long haul, that connect all the data flow channels from city to city. So this is a tremendously useful device, and it falls. It's the most trivial example of our FIR feed forward structure. Okay. So, in terms of this modulator, one more small comment about this. A couple lectures ago, I think, we talked about the modulation property, and people asked, how do you realize that multiplication block? Well, this nonlinear transformation is exactly one way of realizing that input-output multiplication. Okay, so in the optical world, you build a filter that looks like this. It can be operated as a multiplier or as a modulator. And in fact, I should make one more comment about this: the physical realization of this signal, of this function. You start with a waveguide in a piece of lithium niobate. That's a very fancy sounding crystal. But the waveguide breaks off into two pieces, one arm here and one arm here. And then the two waveguides branch back together exactly the way I've drawn it. Exactly the way I've drawn it here. They branch back together. So, and they come back together exactly the way I've drawn this. And on one arm, the bottom arm usually, or actually they sometimes do both, they put a voltage. They apply a voltage onto this crystal. And if you think about this, a voltage is a force, and it starts messing with the crystal structure. Okay, so the voltage puts a force on all the charge clouds and squeezes them together. Okay, they squeeze it. It's like the voltage squeezes these together. When materials get squeezed together, when the atoms get closer together, the density goes up. Right? I mean, we're just a handful of people in a big room, but what if I squeezed us all together into one tiny little center in the section so that we're all scrunched up? Our density goes up. If our density goes up, then the material response goes up, the index of refraction goes up, and the light takes a slower time to go through that branch. If it takes a slower time to go through that branch, it's delayed. Okay? So when they come back together, when these two waves come back together, they come back either in phase or out of phase. And that's the in-phase response and the out-of-phase response, depending on how much of a voltage you put onto this fancy-sounding crystal, this lithium niobate crystal. Okay? And so that is the physical realization of this signal flow diagram, and you can see that it's one for one. You can't get much tighter match between what's going on the physical level and what's going on our signal flow level. Don't get used to that. Okay? Don't get used to that. Because a lot of this is building up towards the digital signal processing world, where you're going to do stuff mathematically that becomes very abstract, and you can program your code and have no real physical realization. So it's really very powerful. Okay? So the divorcing of the limitations of a physical realization can be actually very, very powerful, and that's one of the nice things about DSP, digital signal processing architectures. Okay, I could talk at length about that device, but that's probably enough for now. All right, now, so let's redraw our feed forward block, and we'll try to do that a little bit more generally and a little bit more economically. So I'm going to reuse my Z delay blocks. So this is our first order path. This is our second order path. See, the second order path goes through Z to the minus 1 multiplied by Z to the minus 1. So it sees two delays, two steps of a delay. So I don't have to reuse shift registers or things of that nature if I use this architecture. And I'm going to weight each one of these. Remember, I had little gain blocks, but I'm just going to make my diagram a little bit more elegant. And there's no reason why I have to stop at second order. It's not uncommon to it's not uncommon to design a 100 or 200 order system, especially if it's a finite impulse response or a feed forward system. Okay, filter. Okay, so if I draw the output of this, h of z, and I'll draw it for an mth order system, then this is simply a sum from k equals 0 to m, b sub k, z to the minus k. So I can say that the transfer function is a polynomial. It's order m. It's order m. M is the number of delays. If I factor the polynomial, I get the roots of the polynomial, and the roots are called zeros because at those points, at those z's, the transfer function goes to 0. Okay? So you can see where this transfer function goes to 0 by factoring that. Okay? So this nulls out at 0 is where that's going to go to 0. If I send in a delta function, then out comes m echoes. I'm using that word the same. I'm just using that word casually. So out will come m responses, and then nothing else. And so again, this is an example of an FIR, finite impulse response, feed forward structure. Let me change notation just a little bit. I'm going to call this Hn of z. I'm going to call that Hn of z. Okay? You'll see what the n stands for in a heartbeat. All right, so these are all this is sort of what we've studied so far, the feed forward structure. Let me turn the arrows around a little bit. Let me turn those arrows around a little bit. And we'll consider a slightly different function. And what I'll do is I'll tap off the output and I'll delay the output. And I'll keep going, z to the minus 1. I should draw my arrows carefully so you see the direction of the signal flow. And I can continue down this path as many times as I want, as many delays as I want. So I'll add in some weights. This will be minus A1, that's a delay. And this will be minus A2, and if I go on down, I'll get additional weights. And so if I add all these guys up, then my transfer function and I'll label this h sub d, is equal to 1 over 1 plus the summation k equals 1 to n. So this is for nth order. A sub k z to the minus k. So I'll just emphasize that. N delays. Okay. So now you can see my h sub n and h sub d. One's a numerator, and the other's a denominator. Okay, because all the action is happening in the denominator part of this. Okay. So this is not a polynomial. This is actually 1 over a polynomial. If I send in a delta function, out will come an infinite number of echoes, even for finite n. Even for finite n. Because think about it, a delta function is going to feed back again and again and again and again and again and again and again. And so a single input will give rise to just a steady, a large number of echoes, an infinite number of echoes. And so because of that, we call this not a finite impulse response, but we call this an infinite impulse response. Filter system. And it's because of the feedback structure. So it's not a feed forward, it's a feedback structure. So this polynomial in the denominator, and the roots of that polynomial are the location where the transfer function is going to go infinite. If I happen to be z exactly equal to that root, then I'm going to have a 1 over 0 in my denominator, and that's going to be infinite. And so we call those elements poles. Okay? I think I've used those terms before, and now I'm being a little bit more specific about exactly what they mean and what they are, and you can imagine yourselves calculating these. Okay? Okay, good. Now, let's put both of those structures together. It's going to take us a little bit of time to draw this structure, but let's put them both together. So I'll do the feed forward system first. It's actually not always advisable to do that. So that's our feed forward block. And then the feedback block, tap off here at the output. Minus A1. Minus A2, and all the way down to N order. So this guy here is our feedback block. And we know what the transfer function is of this guy here. And we know what the transfer function of this guy here is. And I'm putting this transfer function in Cascade with this transfer function. So there's a property, I think it's the associative property of these systems. So I have my total transfer function for this as the numerator polynomial divided by the denominator polynomial. So nothing I've done is new. We did the feedback, we did the feed forward, put them together, and now I have a very, very, very general form of a transfer function. And I've also so feed forward plus feedback. And this is called a direct form realization. It's a little bit vocabulary, it needs a little bit of explanation. The premise is this. I can take any order polynomial, I can take any order filter, and I can draw it as a numerator and a denominator of polynomials. Okay? And if I want to build that, then this is the structure. This is the wiring diagram, if you will, to realize that filter. Okay? So here's a couple of points. If I have a desired filter response, in other words, I have a certain input and I want to make a certain output, okay? If I want to have a certain input and I make a certain output, then what I can do is I can decide how good a fit I want to that. So I can pick m equals to 100, n equals to 50, and I have 100 terms in my numerator, and I have 50 terms in my denominator. So I have 150 degrees of freedom that I can use to fit the desired transfer function. Okay? So you can think, if these are polynomials, you can think about all the spline techniques, all the curve fitting techniques, you know, all those algorithms to find the best A's and B's of your polynomial. And that's, in a nutshell, the design problem. And, you know, it's not a pencil and paper kind of a design approach. What you do is you come up with algorithms for writing down, for doing those fits, those splines. And there's not one algorithm, there's a variety of them, and some work better than others in certain situations. And they're all stored in MATLAB. So MATLAB is a repository of 25 years, 30 years of this curve fitting work that helps you design filters exactly this way. FIRs versus IIRs, and so on. So it really opens up a huge amount of opportunity for you just by thinking about your signals and your systems in this manner. Okay? So it's both beautiful and very powerful. Okay? So that's a word on the design problem and the approach that people take on that. So, very general form of the transfer function. I'll remind you that you can factor these polynomials. And that gives you your poles and your zeros. As we did before. And the poles and the zeros describe the filter fully. Okay? So shorthand notations are a vector of A's and B's, a vector of the A's, just a set of numbers, 100 numbers if you want, 50 numbers if you want a 50-order polynomial in the denominator, 100 numbers here if you want it in the numerator. So just a simple vector can describe the entirety of this filter. Or if you prefer, you can draw the vector as poles and zeros. So these are just shorthand ways of capturing all the information in your filter. Okay? Either one. And both are useful and both are used. So you could just a shorthand notation of where are the zeros, where are the poles, what are your A's, what are your B's, and that's the parlance and way you talk about this. Now, I think this block diagram teaches or reminds us of something that we've kind of talked about. What does a filter do to a signal? It splits the signal. It delays those splits. It waits. And then it adds back together. So that's pretty philosophical. What does a filter do? Well, all it does is it takes a signal, it splits it up into components, it delays those components, it weights them, and then it puts them all back together again. That's a very general description of a filter, but it allows you to look around and see filters where they exist. Okay? So it allows you, by thinking about it that way, you can look around the physical world, you can look around your desired algorithm, the data flow that you want, and you can start to classify exactly what what you need to do to build, model, analyze, design, and so on. Okay, so I like that lesson that comes out of this this block diagram and comes out of this transfer function from that block diagram. It gives you a physical interpretation of the actions, of the activities that go on inside that structure. Okay, all right. Oh, I guess just silly little kind of a bookkeeping thing. You'll notice this 1 in here in the denominator, and technically there is a 1 there, but we just write it as a b sub 0. And then we start this summation at 1. Okay, so there's always a unit delay here, and this branch here is this 1. Okay, and so the overall gain of the filter that is at b naught coming through there. Okay, so just a small funny way we choose to write those polynomials. Okay. All right, I want to go back, take a step back now that we've seen this. So I have h of z as the sum of as the ratio of two polynomials. And this is my output of z over my input of z. And so what I'm going to do is I'm going to multiply through. So I'm going to have y of z times my denominator. And I'm going to have x of z multiplied by my numerator. And I'm going to write my output in terms of the previous outputs plus all my inputs. So I've just rearranged my equation a little bit. I'm making use of that 1 that I mentioned just a moment ago. So just to remind us of what this is the output of the device for a given input. And this is the previous outputs. And this is the weighted sum of current and previous inputs. And now I'll go back. Now I'll go back to our very beginning, where we looked at the difference of a signal in the z domain and in the time domain. Okay? And I'll transform this back so that this guy here will transform to a discrete time signal y of n. That's still my output. My z to the minus k's tell me how to place my delta functions. So I go back to the time domain. So these LTI systems are described by a constant coefficient. And if you look at this, this is a difference equation. Okay, so if I have an LTI system, and if it's described by constant coefficient difference equations, then it has a rational system function, h of z, written as a summation of, as a ratio of two polynomials. Okay, so let's do a quick example. I don't know if you've heard of or remember the Fibonacci sequence. It's kind of one of these fun little math facts that you run across, and engineers and mathematicians, they remember these things, and the rest of the public doesn't. You know, but it's kind of a fun little toy problem. It shows, you know, the reproduction of fruit flies, for example, in a petri dish, things of that nature. Fibonacci sequences are there's a Fibonacci journal, a journal of Fibonacci sequences, and it's actually published out of a monastery in California. And I think the premise is that because Fibonacci sequences are found everywhere, people say in sunflower seeds and in the patterns of mollusk shells and everything like that, that there's something very otherworldly about the Fibonacci sequence. Okay? If you feel that way, I may end up bursting your bubble. But so the Fibonacci sequence, let's remind ourselves what it is. If I start with a 0 and I start with a 1, okay, those are, we can think about those as our initial conditions, or our seeds for generating a sequence. Then the next sequence is 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13. And 21, and so on. And these are the Fibonacci numbers. Okay? So this guy here is 0 plus 1. This guy here is 1 plus 1. This guy here is 1 plus 2. This guy here is 2 plus 3, and so on. And if you think about that, what this is an exponential increase. Okay? This is an exponential increase. If I change the signs on these, I can get an exponential decrease. If I change the signs in a different way, plus then minus, I can get this alternating. Okay? So in the same way that we talked about Fourier series as taking a basis set of sines and cosines, or complex exponentials, and constructing any function that we wanted, well, the Fibonacci sequence is exactly a basis set. It's a real exponential. And so I can find any pattern and I can fit it to some few terms of a Fibonacci of modified Fibonacci sequences, and I can describe those patterns of the mollusk scales, all this stuff. Okay? So the Fibonacci sequence and its use in its mysticism is an example and reminds us a little bit of our Fourier series work in taking any old sequence, any old signal, and rewriting it as an exponential. And I won't make too big a difference between a complex exponential and a real exponential because, hey, there's just sign changes and small stability changes. Okay? So there's a little bit of a down-to-earth kind of editorializing on my part, but I came up with, and maybe I'll share a little bit of this later on, but I came up with, in my work, things like the golden mean and Fibonacci sequences, and I thought for a moment about publishing it in this Fibonacci journal. And at the time, it was delivered by mimeograph. So even in the 90s, they were printing the Fibonacci. The monks were printing the Fibonacci on an old-fashioned mimeograph. I don't know if you knew that, if you've ever seen those machines, but they're in the old days. If you wanted a copy, you would draw your whatever you copied, and then you'd crank through. And there was a printing process called a mimeograph, and every school office had one. That's how you commute. That's how tests were Xeroxed, or it was, tests were copied and everything. So it was very old, very, very, very old school. I haven't seen one in years and years. All right, I digress. I'm sorry. Let's go back to this rule on how exactly this is described. Y of n is equal to two previous outputs and two previous states. Okay, so this is the rule. The output is equal to a prior output plus the output 2 cycles ago. Okay, so this is a second order difference equation. And fits the form that we looked at before. Yn is equal to 2 of these terms and none of these terms. Okay? So y of n is equal to 2 of these terms and none of these terms. It's an unforced or homogeneous difference equation, if you want to think of it that way. And we have to be a little mindful of our initial conditions. So our b sub k's will all equal 0. And our a0 is equal to 1. Well, we won't write that. We'll just write an a1 is equal to 1 and an a2 is equal to 1. So rather boring when I write it that way, but that's just the nature of this magical set of numbers. And we do want to be mindful of our initial conditions. Y of 0 is equal to 1, and y of 1 is equal to 1. Actually, y of 0 should be equal to 0, right? Sorry about that. And y of 1 is equal to 1. And those are enough to generate all these. So if you change the initial conditions, you can do anything you want with the sequence. Okay, if you change these minus signs here, you can do even more things. So there's no numerator, so I'll just put a 1 there. And 1 minus 1 times z to the minus 1 minus 1 times z to the minus 2. That looks a little clunky, so I'll just write it again. A little more simply. So there's the h of z. And you can imagine the signal flow diagram following directly. Okay. Now I said that we could factor this. So let me give you a quick example of that. So I'm going to multiply through by z squared over z squared. And so what I'll have is this will equal z squared over z squared minus z minus 1. So this will equal z squared, z minus pole 1, z minus pole 2. Okay? So second order system characterized by two coefficients, an A1 and an A2. So my vector here will be 1, comma 1. That's my A vector. And I could also write this as a vector P1 and P2. Okay? And what I have to do is I have to factor this. Well, this is a nice little second order second order polynomial. So it's negative of b plus or minus the square root of b squared minus 4ac all over 2a. So my two poles, my two roots of this is 1 plus or minus the square root of 1 squared minus 4ac, which is just 4, all over twice the first coefficient of a. And this is equal to 1 plus or minus the square root of 5 over 2. And that's your mystical golden mean. Right? So that's where that comes from. Okay? So looking back over this fun little math club problem that you guys had in high school, we can now understand it in terms of these digital filters and digital signal processing, and in the context of even more elements of the course. So kind of cool, kind of neat, I think. Okay, so that's one example, and we'll do a few others as we go along as well. Okay, so I just want to I talked a little bit about the design or the synthesis problem. And I just want to go back to that. Just to get it sort of formalized a little bit. So what we want to do is we want to take a desired or a prescribed filter response, and we see the problem now as expressing the output and the input, the numerator and the denominator, as polynomials. Okay. So the kinds of things that we think about spline, fits, curve fitting. Those are all algorithmic. Perhaps a Taylor series. And all these are algorithms on something like a package like MATLAB. MATLAB and more LabVIEW, as LabVIEW goes from pure instrument control to post-processing of the data that the instruments take. Okay, so you see they're kind of coming together, fighting each other in the marketplace, really, if you want to look at it that way. So, if I were to say one is better than the other, I'd be taking a business statement. And what's the freeware version? What is it? How do you spell that? I think it's Scilab. So, that's probably, being a cheapskate, that's probably one that I would, go to. We're spoiled here because we have access to all the software we need in our labs. But when you get out in the real world, you will recognize that MATLAB and LabVIEW are hideously expensive. And so, especially if you're starting your own company, you don't want to, throw a lot of money into software tools. Okay, so fit this and then realize the filter. By programming the weights of the specific delays. Okay? So really, really straightforward. And so in MATLAB, once you have these structures, again, you can hook your computer directly up to the DSP, to a DSP chip, and transfer your MATLAB code directly onto it'll compile. There's a compiler that will take that MATLAB code, that .m file, and put it right onto your DSP. Okay? Small warning that that's usually an inefficient compiler, and it so it may run a little slower, and it may be a little clunkier, and there may also be some little aberrations. So what most people do is they'll compile it, and then they'll clean it up and end up reprogramming a lot of it in C or C++. So it's not that, it's if you want to do something fast and quick and dirty, it's great. If you want to do something a little bit more careful, more elegantly, then you should take a step back. Okay. Let's see. All right. Okay, so let's sorry. So let's be a little more general than our Fibonacci example. H of Z, numerator of Z over denominator of Z, and B0 plus B1 Z to the minus 1 plus ... Bm Z to the minus m, divided by the denominator, A0 plus A1 Z to the minus 1 plus all the way out to AN Z to the minus n. Okay? So slightly different notation than I had before, but not terribly. And so now if I factor this, or if I rewrite this, factor out a Z to the minus m, factor out a Z to the minus n, also pull out the B naught and the A naught, then this term here okay, so now, yell at me if you, I have a little bit of feedback there, but I tend to not see it too often. Okay. So if I factor this a little bit, or at least figuratively factor it, this leading term, I'll just clean up the minus m and the n. And then my zeros look like this. And my poles So all the zi's are the zeros. And just to remind you, that's where the transfer function goes to 0. And all the pi's are the poles. And that's where the transfer function goes to infinity, or we can call that a resonance output. That's a nicer term for it. It hides the singularity a little bit better. And so there's a gain associated with the filter. That's this B naught over A naught. There's a set of zeros. And these are often called trivial zeros. And they represent the overall delay through the device. Okay. And then I will rewrite this product using that product symbol. K equals 1 to M of Z minus CK. And again, a product symbol. K equals 1 to N of Z minus PKs. So M zeros, N poles, and these fully describe the filter. And this is called a cascade form, or a cascade realization. And if you want a picture to go with that, you have something that looks like that. I guess actually I should take it out this way.